Okay, physicists, we are getting ready to embark on one of our single biggest and most important topics in all of IB physics. Topic 2, which if you refer to your IB physics guide, is called mechanics. It encompasses motion and kinematics. It encompasses forces and dynamics, work, energy, and power, and momentum and impulse. And the first two, motion, or kinematics, and forces, these are two of the most fundamentally important topics in all of IB physics. And the reason is because we basically use the ideas that we're going to learn in this topic for the entire 2-year course in almost every single other topic. So it's kind of like vectors in a way, where it's like we learn it, but it never really goes away because we keep applying it over and over and over. Okay, so super important, this series of videos coming up. Really important for you guys, and we're going to spend a long time on this topic. Okay, so the first thing that I want to just point out to you is that in our studies of motion and kinematics, just to give you an idea of how important this topic is just to remind you that everything in the universe is moving all the time. In fact, it's really the only constant of the universe is that everything is moving. And the other way of saying it is that the only constant thing in the universe is the fact that things are constantly changing. I don't know if you've ever heard that term. So in this video, which is a time-lapse, nighttime time-lapse from a campsite on top of a mountain with a lake and the Milky Way in the background, there are lots of things moving. And the most dramatic thing that's moving are the clouds and the sky. Now, an interesting thing to just stop and think about, if I were to ask you to figure out how fast these objects are moving, how would you do that using the video? Well, a couple of things. You would need to know a scale. You'd have to have like a length scale in the video. You have to know how many pixels are represented in, say, 1 meter, for example, which is quite difficult because the clouds are a lot closer than the stars in the Milky Way, obviously. The other thing you'd need is you'd need a time. You'd need to know the time between frames. And the other issue that you have is one of parallax, because the scale for 1 meter on the horizon is quite different than the scale of 1 meter for the clouds here. So anyway, the point is that it's quite difficult to actually sum up, to quantify motion. We're going to try to. We're going to make a lot of simplifying assumptions when we do so. Okay? All right. So the first thing I want to do is just sort of formally define kinematics for you. And kinematics is simply the study of motion, okay? And if you think about the easiest thing to measure, right, it's probably how far something moves in a certain time, a distance, right? Like, for example, like dropping something, okay? Now, to measure how far something drops, you need a zero reference point to start from. So, say if I drop this pen, okay, and if I define my distance equals 0 to be right at the very beginning when I start my timer, for example, when t equals 0, then that's a very convenient way to measure the distance and the time while that pen is dropping, okay? So usually the initial time is 0, but not always. And basically it's up to you as an experimenter to decide where you want to even measure the distance from. And here's this really cool video of a steel ball falling into a sort of a vat of really fine sand, kind of like sawdust. And again, as you watch this video, isn't that cool? All the bits of dust coming back down, and then the ball comes bulging back up out of the surface. I want you to think about how you would measure, how you would quantify the motion of this ball, right? You'd need to know a distance, you'd need to know the time between frames and so forth. There's tons of really cool slow motion videos on the internet of people dropping things and things falling and whatever. Super cool. We can watch some of those in class and kind of comment on them. I have a few of my favorites I can show you. Anyway, you should check it out, okay? So if you can measure the distance and time taken for something to go any distance at all, you can figure out what's called the average speed of an object. And the average speed is just simply the total distance traveled over the time taken to travel that distance, okay? All right, so I'm going to make a couple of very fine distinctions between some terms that you may have heard, you may not have heard, Anyway, these definitions I come up with are very specific. And for example, there's a big difference between distance and displacement, and I'm going to explain it to you right now. Okay? So distance is simply how far something is from something else. Usually given the variable s, okay, we don't use little d for distance anymore. We use the variable s, okay? And distance, what's important to know about it is that it has magnitude, but it does not have direction, so it's a scalar. It's a scalar. And the SI units for distance, the same as for length, it's just meters, okay? So, for example, I have two objects. They're both starting off at the origin, a blue cloud and a red heart, okay? The red heart moved all the way over here to being 10 meters away. So we say the total distance traveled by the red heart was 10 meters, okay? Now, the blue cloud looks like it traveled 6 meters in this direction. Notice I'm actually showing the distance that they traveled by vectors, okay? And as you can guess, the vector the vector representation of distance when you add direction is called displacement, okay? Now notice that both objects started at x equals 0, okay? And here's my definition for displacement. So how far something is from something else in a certain direction. Usually we give it the variable s, but it's s as a vector. Notice that it's bold, okay? So s vector is displacement, and s without a vector is just distance. So it has magnitude and direction of vector, but its SI units are still meters, okay? So in this case, very obviously, I would say, well, my displacement vector for the blue cloud is negative 6 meters, and my displacement vector for the red heart is positive 10 meters, okay? Now, if you think about, like, let's say that you're on an island, okay, and you want to get from A to B, between A and B, okay? Well, if the black line here represents the road, let's say it's quite mountainous, and you can't build a road from A to B, okay, then clearly the road is a lot longer than the straight line distance between A and B. So for example, if the displacement between A and B is 5 kilometers, then you know that the distance between A and B is a lot greater than 5 kilometers. So just think about it as a straight line, or kind of as the crow flies, if you've ever heard that expression, or just a tunnel bored through the mountain. Think of that as the displacement. It's a straight line between 2 points, whereas the distance would be the actual path taken to get there, okay? So along the road is much longer than 5 kilometers in this case, okay? All right, here's our first example. It's going to seem straightforward at first, but it can get a little bit confusing, so you have to really pay attention to my explanation of these solutions. Go ahead and pause the video and read it. Okay, so I have a mass initially at negative 1 meter, and it moves 3 meters to the left, and then 5 meters to the right. So I'm asking you two questions. What's the total distance covered by the mass, and what's the change in displacement, okay? Well, I've drawn my displacement vectors here, okay? So here's my little I hat vector, and on both, okay? So I have S1 is negative 3i, and S2 is positive 5i. So notice that it started at negative 1, which is what I'm given in the problem, okay? So the total distance, well, that's pretty easy. That's just 3 meters plus 5 meters, which is 8 meters, okay? All right? Now, I want you to think about the total displacement from where it started. To find the total displacement, that's just the resultant vector of S1 and S2. So it would be negative 3i plus 5i, okay, positive 5i, which is positive 2i, which is positive 2 meters. But notice this is not where the object actually ends up. If you look at the diagram, the object obviously ends up at 1 meter, positive 1 meter, okay? So the other thing I want you to notice is that the change in displacement is the final displacement minus the initial displacement. This is also, turns out it's the same as the total displacement from where it started, okay? So I've indicated the change in displacement, which itself is a vector, as positive 2i. Notice that in neither of my answers do I actually answer the question, where does it finally end up, okay? So where it finally ends up is at positive 1, because its delta S, its change in displacement, was positive 2. So positive 2 in the x direction, okay? Okay, so here's my same diagram I had before, the red heart and the blue cloud, and I'm going to define to you speed and velocity now. It's very, very important to understand what the differences are. Now, you probably know that speed is the change in distance over change in time. We call it the variable v. We do not use the variable s for speed, so please never do that. That's one of those cardinal sins in physics. You want to always use v. Speed has direction, has magnitude, but no direction. Its units are meters per second, and it's simply v equals s over t, or delta s over delta t. If I start at s equals 0 and t equals 0, I can get rid of the deltas and just call it s over t. Okay, so in this case, all right, I have a displacement going from, with the red heart going from 0 to 10. Okay, if that displacement takes place, for example, in 2 seconds. Now I just pulled that 2 seconds out of the air. Okay, I said if it covers its 10 meters in 2 seconds, then its average speed is 5 meters per second. Okay, now for the blue heart, okay, or the blue cloud, if it also covers that distance, it's now in this case 6 meters in 2 seconds, then its speed is 3 meters per second. Notice that in neither of these expressions gives any indication of the direction in which the object is moving. Okay, that's for velocity. That's what we're going to talk about in the next slide. Okay, so velocity is just speed in a certain direction. It's a vector given the variable v as a vector, right? Okay, which is a boldface type if you're typing it. Okay, the only thing different between this equation and the one before is that now I have vectors. V is a vector, and I'm using displacement over time instead of distance over time. Okay, units are still meters per second, so don't worry about that. That's very, very easy. Okay, so now in this case, you guessed it, the velocity vectors would then have positives and negatives associated with them. So now my velocity vector for the red heart would be a positive 5, indicating it's going to the right-hand side. Okay, and for the blue cloud would be a negative 3, indicating that it's going to the left-hand side. So very important that you understand the difference between those two. Okay, all right, so just a couple of examples of cool movies. These are so cool. Check this out. This is a slow motion video of a bullet hitting a wall. Isn't that cool? So if you had a scale, like a length scale, you could actually figure out a lot of things from this video. You could figure out its average speed between this point and the point that it hits the wall. You probably don't have a high enough resolution of frames to figure out what its acceleration is, which is obviously negative. It slows down very, very quickly. Anyway, it kind of spreads out and becomes deformed. Okay, a lot of times when you take a video, you have things like the interval between frames and the frames per second and so forth. Okay, here's another video of the space shuttle being launched. Okay, so I just want you to think when you're watching this video how you would figure out the average speed and eventually the average acceleration of this spacecraft, which is accelerating off the surface of the Earth. Again, parallax is an issue because the spacecraft appears to be a different size as time goes by and as the video camera pans out. Here's another one. Here's a dude shooting a basketball. We will talk about projectile motion in detail, okay? But again, if you know the time distance between frames, or the time difference between frames and say the height of the guy, you can use a program called video physics, which we will use to actually analyze that motion and figure out exactly how fast it's going, what the acceleration is, and so forth. It's pretty cool stuff, okay? So this is what you'd need in each video if you wanted to measure velocity, okay? All right. Okay, we're going to do a couple of examples. This one might look familiar to you guys. I hope it is. So I'm not going to actually pause it unless you want to pause it and try. Yeah, try this again. Okay. So we have this object on a string moving in a circle of a radius 3 meters with a constant speed of v equals 6 meters per second. However, the velocity changes constantly, even though it has a constant speed. Why? Because it's changing direction. It's at all times tangent to the circular path as shown. We will spend a lot of time later talking about circular motion, so don't so much worry about the physics of this right now. Okay. I'm asking you to find delta v, which itself is a vector, and that's vb minus va. Okay. So vb minus va is really vb plus negative va. It looks like this. Okay. So here's my negative va. Here's my VB. All you do is you add them together. Your resultant vector is this vector right here, which is pointed directly towards the center of the circle. Okay, and I use the Pythagorean theorem to find that VAB. The speed is 8.5 meters per second, and the direction is clearly 45 degrees below the negative x-axis. Okay, all right. Now, to do delta v between B and C, very, very similar idea. Notice that the resultant vector, again, is pointed right towards the middle. Okay, because acceleration is delta v, is the change in velocity over the change in time. This is proof that there is a constant acceleration towards the middle of a circle of something moving in circular motion, and therefore, there's a force acting towards the middle of a circle, and that's called centripetal force, and it's due to centripetal acceleration, which is the change in velocity vector from the outside. For any object moving in a circle, the change in velocity vector is always pointed towards the middle of that thing. Okay. Now, I have this summed up for you. I have that the velocity constantly changes because its direction is constantly changing. Speed does not change, and delta v points towards the center of the circle, which of course means that there's an acceleration towards the center of the circle, and we call it centripetal acceleration. Okay? All right. So there's a positive velocity if the displacement is increasing. There's a negative velocity if the displacement is decreasing. Think about that. Okay? So we refer to the initial displacement as s naught and the final as s. These should both be vectors. Okay? All right. Then the velocity is the change in displacement over change in time, which is s minus s naught over t minus t naught. Okay? All right? Now, if the change in displacement is positive, it's a positive velocity. If the change in displacement is negative, it's a negative velocity. We don't have to worry about our denominator being negative because time can never be negative, and a time interval can never be negative because you can't end up with a final time that's less than your initial time because time only goes in one direction. Think about that for a second. Okay? Now, if t naught equals 0, all of this reduces to s minus s naught over t, right? Because of what I just said. If you start t at 0, so if we rearrange this, we come up with this pretty nifty equation for displacement, and the displacement is s naught plus the velocity times time. Okay? And note properly that if the velocity is 0, it's pretty boring, the thing is not moving, then s equals s naught, which is exactly what you think it would be if you just think about it logically and rationally. Okay? Now, back to the space shuttle. You have to be really careful if you're asked a question like this. Okay? And I was reading an article about the space shuttle, Endeavour, and you know all the space shuttles have since been retired. Okay? But the space shuttle Endeavour over a 19-year time period flew, wow, 1.98 times 10 to the 8 miles. Actually, is that kilometers or miles? I think that's actually kilometers. That's a lot, okay? What was its speed? Well, that's actually a ridiculous question, right? Okay? Just because it existed for 19 years doesn't mean it was moving the whole time. In fact, it was not moving the whole time. Even if you knew that the time spent in space was 296 days, 3 hours, 34 minutes, and 2 seconds, all right? You still couldn't answer this question, right? Because it's constantly speeding up and slowing down and whatever. I mean, to say that's its speed, like you don't have enough information. Okay? Just to remind you, what reads on your speedometer on your bike or your car is your instantaneous speed. Okay? It's not instantaneous velocity. Your speedometer doesn't tell you in what direction your car is driving. It's your instantaneous speed. And this speed is not the same as your average speed for the whole trip. If you think about it, if you're driving from Ocean Beach to AT&T Park any time of day, do you ever have the same... Are you keeping the same average speed the whole time? No way. You're speeding up, you're slowing down, you're stopped half the time, especially if it's during rush hour. So the average speed for your whole trip would be your total distance divided by your total time. It tells you nothing about how fast you're going at any one instant of time during that delta t.